This video will discuss creating a network model for the supply chain network shown in this diagram. This network has 3 factories, 2 distributors, and 2 wholesalers. The problem facing the company is how to effectively ship units from the factories, possibly through the distributors, to satisfy demand at the wholesalers. In the diagram, each of the arrows represents a possible route in the network. The first thing we'll do, noticing that there are 7 locations in the network, is create an index that identifies these locations by number. The list of locations is shown here on the screen. We usually call these locations in the network diagram nodes. Each node has a description. The factories are nodes 1, 2, and 3 in the network. The distributors are nodes 4 and 5, and the wholesalers are nodes 6 and 7. To create the Excel model, we make a list of all the routes in the network. This is shown in columns A and B, as noted with the descriptions origin and destination. Each line represents a route in the network. Line 8 represents the route from node 1 to 2, which is a route from factory 1 to factory 2. As another example, line 11 shows a route from node 1 to node 5. Node 1 is factory 1, node 5 is distributor 2. The unit cost in column C are the costs of shipping each unit on those routes. Cost will vary due to many factors. Could be the location between the nodes, but also could be the availability of shippers to be able to drive those routes. The decision variable in this model is called the flow. The flow is simply the number of units shipped on each route in the network. To begin the model, we'll just give the flow a starting value. We'll ultimately use Solver to change this flow to try to minimize the cost for the company. In column F, we have a constraint on the maximum number of units that can be shipped on any route. Right now that constraint is set to 200, but we can certainly change that constraint if we have different maximums on different routes due to different shipping companies and different truck sizes. At the bottom of the screen, we have the total cost cell, and this will become the objective in Solver. The total cost is simply the number of units shipped on each route times the unit shipping cost on that route, with the total of those all added together. Excel has a built-in function called SUMPRODUCT that's very useful for calculating this total cost. We would calculate the sum product of all the unit costs in column C and all the units shipped, or the flow, in column D. What sum product does is multiply each unit cost and unit shipped individually and then total up all of those products, a sum product. To the right of the screen, we have the cells where we will create the constraints in the model. We saw on the diagram, and it's also shown in the worksheet, the different capacities at the factories and the demand at the wholesaler. The wholesalers would serve the customers or the retail stores farther down in the network. To build the network model, we need to calculate the outflow for every node and the inflow for every node. The outflow is based on a route where that node is the origin. The Excel function SUMIF provides a very good way to build this outflow formula. SUMIF requires three quantities: the range of cells to be evaluated, the criteria, and the sum range. In this case, we want to evaluate all of the origin cells, and I want to build that with an absolute reference. The criteria we want to evaluate is the node, and the sum range is the number of units shipped, sometimes called the flow. What SUMIF will do in this case is go out and evaluate the origin cells and find any origin for node 1, and then sum up the corresponding cells in the units shipped. This avoids us having to go build a separate formula for each node to sum up the flows on which that route, on which that node is an origin. The inflow formula is similar, except that inflows are associated with destinations. The range to evaluate then are the destination cells with an absolute reference. The criteria is the node for the row that I'm on, and the sum range is the units shipped or the flow. Inflows are the units shipped into a node. Outflows are the units that leave the node. I want to be careful to have absolute references on the range and the sum range, but not the criteria, and this will allow us to copy this formula down to all the other nodes. We can also copy this formula to the distributor nodes and the wholesaler nodes. Once the outflows and inflows are established, we need to calculate the net flows. To calculate net flows, we do have to treat the factory slightly different from the other nodes in this network. One thing that's very important to notice is that in this network, our total plant capacity at all plants is 600, and our total customer demand is 580. We have enough capacity to meet demand, and that will be important when building the constraints. Factories are locations where typically we expect shipments to originate from. While we do have options to ship nodes between factories in this network, we expect that in total we should have more units leaving the factories than we do being shipped there. Because of that, our net flow will be the outflow minus the inflow. We would expect to have more outflows than inflows at factories because the factories primarily produce the goods. Again, factory net flow is outflow minus inflow. Net flows for distributors and wholesalers are treated slightly differently. Distributors and wholesalers don't produce the goods, so we would expect generally more inflows than outflows at the distributors and wholesalers. In the case of distributors, it's possible that inflows and outflows could be exactly balanced, and we may want to force this with a constraint. But we would expect net flows typically to be zero or positive if we take inflows minus outflows. Inflows are usually at least as big as outflows. Same is true of the wholesalers. The wholesalers are the locations that ultimately will satisfy the customer demand, so we expect inflows minus outflows to be positive. That's what allows us to satisfy the customer demand. So far, we've identified the decision variables. We've built cells to balance the flows at the different nodes, and now we're ready to use Solver and implement these constraints. To build an optimization model in Solver, we first need to identify the objective. In this case, the objective is to minimize the total shipping cost. So we have to identify the total cost as the objective. We want to be sure to select minimize. The changing cells are the flows in the network. So we need to highlight all of the flows in the network. The flows are the units shipped. We have some different sets of constraints. The first constraint we have is that the maximum number of units shipped in the network is 200. So we need all of the flows to be less than or equal to the maximum. We do have the ability to change the maximum on each route individually, and that may be important for some applications here. The other constraints are related to each type of node in the network. The net flows at the factory cannot exceed the capacity at the factory, so we have to have net flows less than or equal to capacity. Right now, we are assuming that the distributor balances its flows exactly every month. If there is any inventory at the distributor, it would be a safety stock type of inventory that's already in place. So the net flows at the distributor will be equal to the required flows, which for now is 0, because we want to balance inflows and outflows. The wholesaler constraints deal with customer demand. In this case, because we have enough capacity, we will exactly equal or exactly meet customer demand. So the net flows into the wholesalers are equal to the customer demand at the wholesaler. We want to make sure in this model that the solving method selected is simplex LP. And it may default to one of the other methods in your solver application, but we want simplex LP. We click Solve, and the minimum total cost is $32.60. We'll eventually look at several ways we can adjust the constraints in the network model to deal with different problems or different constraints that companies may face.